we said was that if the partial sums look something like this is capital N, and if this is Sn, and if the partial sums are going, are oscillating with smaller and smaller oscillations like this, then we want to use the Shanks. Okay? That was the trick that we used. But suppose the partial sums are not doing that. Suppose, for example, that the partial sums look like this. Here's n. Here's the partial sum. Suppose the partial sums are sort of monotone increasing toward a limit like this. Okay, that's typical kind of behavior of many series. So here is the sum of the series, S. Okay, and you can see that the partial sums are converging like that. What's a simple example of a series that behaves like this? Well, say the sum from n equals 1 to infinity of 1 over n squared. Okay? So the sum or the reciprocals of the squares of the integers. Do you know what the answer is? Pi squared over 6. That's right. This is a very famous series. Okay? If you want to be really fancy, you can say this is zeta of 2. Okay. Don't have to be so fancy. Okay, but this series is pi squared over 6. To show that this is true using freshman calculus is not trivial. Okay, that's a very hard series to evaluate analytically. You can do it, and if you're interested, I'll show you sometime. Okay, but suppose we have this problem. The question is, the most naive thing you could do would be just to put this on a computer and start adding it up. How efficient is that? What's the error? Okay, and how fast does the error decay as n increases? So that's a very simple question. Suppose you have calculated Sn. What is the difference between the sum of the series and the nth partial sum? Okay, that's the error. Okay, that is the amount by which your calculation, by adding up the terms in the series, and the exact answer, how much they disagree. Okay, so this thing is the sum from n plus 1 to infinity of 1 over n squared. Okay, but we can calculate this with tremendous accuracy by just approximating this by an integral. Right? So this guy is just the integral from n plus 1 to infinity of dn over n squared. Okay, actually, it's asymptotic as n goes to infinity. Okay? And this, the integral of dn over n squared is minus 1 over n. You evaluate it at the lower n point, and this is 1 over n. Okay? It's really 1 over n plus 1, but 1 over n is asymptotic to 1 over n plus 1. Okay, what's the difference between n and n plus 1? Between friends, I mean. Okay, so what this says is that if you add up 1,000 terms in the series, the answer is only accurate to one part in 1,000. Okay, if you add up 1,000,000 terms, it's only accurate to 6 decimal places. That's not very impressive. So the question is, can we do better? Yes, we can. Instead of using Shanks, let's use something called Richardson. Okay, this is called Richardson extrapolation. So Richardson extrapolation is a technique for extrapolating a sequence S sub n, somebody gives you a bunch of terms in a sequence S sub n, and extrapolating to the limit of that sequence. Okay? So how does Richardson do it? Again, Richardson makes a model. Richardson says, well, I'm going to guess that S sub n has an approximate form as a series in powers of 1 over n. So, for example, S sub n is its limiting value plus, let's say, a over n, plus b over n squared, plus c over n cubed, and so on. Okay? So that's the model that Richardson makes. Okay? And the question is, what can we do with that model? Okay? So the first thing we can do, let's see. Can we do this? Okay, first thing we can do is to say, let's suppose n is very big. Okay? If n is very big, then these terms don't really matter that much. Okay? So that says that Sn is approximately S plus a over n. And also it says that Sn plus 1 is approximately S plus a over n plus 1. Right? Now, we don't care what a is. We only care what S is, the limit, the behavior of this sequence as n goes to infinity. So it would be nice if we take two equations with two unknowns, little a and s, and eliminate a, calculate s. So how do we do that? Well, there's a very quick, efficient way of doing that. Take this first equation and multiply by n. So that says that n, Sn, is approximately n times s plus a. And take the second equation and multiply it by n plus 1, and that gives you n plus 1 times Sn plus 1 is n plus 1 times s plus a. Okay? And now, all I need to do is, let's raise this some more. So all I need to do is subtract the top equation from the bottom equation. And what I get is that n plus 1 times Sn plus 1 minus n times Sn is s. Okay? So that's a formula for extrapolating to the limit of a sequence. So what you do is you take the n plus first term in the sequence, multiply it by n plus 1, take the nth term in the sequence, multiply it by n, subtract, and there's a formula for the limit of the sequence. Yeah?
So we get an equal sign because you had a multiplier.
Well, I mean, we can call this, okay, I won't call this S, but what I'll call this is R1, okay? R for Richardson, and 1 because I took just the first correction, okay? And the statement is that R1 is asymptotic to S as n goes to infinity. That's the hope. Okay, so I'm glad you stopped me there. Okay, so I think this is a more proper way of writing it. Okay, so we'll define that as R1. And R1 means the first Richardson of the sequence. First Richardson extrapolation of the sequence. So what if we want to do better? What if we'd like to do better? Well, if we want to try to obtain a better approximation, why don't we include A and B, not just A, but the B term in the sequence? Let's see what happens. Okay? So we have the equation Sn is S plus A over n plus B over n squared, and Sn plus 1 is and so on, and Sn plus 2 is and so on. Okay? And then what we'll do is, in the first case, we don't want A or B. right? We don't care about A or B. We're only looking for S here. So let's multiply the first equation by n squared this time. Okay? So that will give me n squared Sn is n squared S plus an plus b. Then let's take the second equation and multiply it by n plus 1 squared. Okay? That gives me n plus 1 squared Sn plus 1 is n plus 1 squared S plus a times n plus 1 times b, or plus b. And the next one will multiply by n plus 2 squared. So that gives me n plus 2 squared. Sn plus 2 is approximately n plus 2 squared S plus a times n plus 2 plus b. All right. Now, are you clever? Do you see a really quick way of solving this equation for S? What do you recommend? I see you're nodding your head yes. What do you recommend?
N plus S, n plus 2 minus 2s, n plus 1.
Very good. Very, very good. So that's excellent. Okay? So what you're saying is multiply this guy by 1, multiply this guy by 1, but multiply this guy by minus 2 and add them up. Okay? So what do we get? On the left side, we have n plus 2 squared Sn plus 2. Then minus 2 times n plus 1 squared times Sn plus 1 plus n squared times Sn. Now, what happens if we do what you say? Let's look at what happens. First of all, you have 1b and 1b minus 2b's. Great, they cancel. Okay? Now, look at the a terms. You have 2 of these, okay, which gives you 2n plus 2, okay? And then you have an n and an n plus 2. Ha! Again, they cancel. They exactly cancel. Okay, so the b's drop out, the a's drop out. Okay, now what about this? What do you get if you take one of these and subtract 2 of those? What are you left with? Say it again? No. Take one of these, n squared, one of these, n squared plus 4n plus 4, and take away 2 of these. Say it again? Just 2. Just 2. So you're just left with 2s. So we divide by 2. Divide by 2, and you're left with s. Okay, except we won't say this is equal to s. We'll say this is equal to the second Richardson extrapolation, which is asymptotic to s as n goes to infinity. Okay? Now, let's see. If I were to divide this by 1, and I divide this by 2, can you guess what the formula for the third Richardson extrapolation would be? I mean, do we have to go through all this mess? Let's see if we can guess. What would you say R3 would be defined as? Okay, so let me just write what you're saying. So you say n plus 3 cubed, okay, Sn plus 3, minus 3, very good, minus 3, 2 cubed, okay, n plus 2 cubed, Sn plus 2, plus 3, Very good. So you see the pattern. N plus 1 cubed S n plus 1 minus n cubed Sn. And then we're going to have to divide by something. By 3 factorial. That's right. 6. That's right. So do you see all the numbers in here? These are just the binomial coefficients, right? This is 1, 3, 3, 1. The next one would be 1, 4, 6, 4, 1 with an alternating sign. Okay? Why is it that an n factorial appears over here? Because when you do a calculation, if you have a function of n, let's say f of n, if you calculate f of n plus 1 minus f of n, this is very much like the derivative of f. This is like f prime of n. In fact, this is asymptotic to the derivative as n goes to infinity. Okay? If you have a reasonably smooth function of n, which we do because these functions of n are just polynomials. So they're smooth functions. If you want to calculate the discrete equivalent of the second derivative, that would be f of n plus 2 minus 2f of n plus 1 plus f of n. Okay, just nothing here. Okay, so that's the second derivative. And if you take the second derivative of n squared, that is 2. Why is it that everything cancels out? Why does the a term and the b term cancel out? Because we have taken the second derivative of a constant, which is 0, or the second derivative of a linear function, which is 0. But if you take the second derivative of the square function, you get 2. That's why we had to divide by 2. If you take the third derivative of the cube function of x cubed, you get 6. That's why we had to divide off 6. Okay? So these are the Richardsons, and if we take more and more Richardsons, we should get better and better approximations to the limit. Okay? So let's see. Maybe it works. Maybe it doesn't work. Let's see. Let's just do an experiment. Okay, I showed you these. Okay, so Richardson extrapolation. Let's see how well it works. So, here. Okay, so we know that this series here, this series that we're calculating, we know that it's pi squared over 6, and pi squared over 6, roughly speaking, is 1.6449340668848. Okay. Now, notice that apart from the 1, I'm keeping 12 places. In order to get 12 places accuracy, you would have to add up, okay, 10 to the 12 numbers. That's hard to do on a pocket calculator, okay? On the other hand, what I'm doing here is writing down the nth partial sum, okay? And here's what you get if you this is the 0th Richardson, okay? This is the Richardson 0. Okay, so if you add up 1 terms, you get this, and if you added 5 terms, if you add up 25 terms, just direct adding up 25 terms in the series, you get 1.606. So for 25 terms, you get really, if you round it off, 1.61, and the answer is 1.64, so you're off by 4 parts in 100. 160. That's crappy. Okay. If you do the second Richardson already knows the answer to one part in, well, one part in 1, 2, 3, 4, 5, one part in 6 figures, one part in a million, just from 25 terms in the series. But if we use the fourth Richardson, then this is what we get. And if we use the sixth Richardson, this is what we get. Okay? So let's see. This is 848. Here's an 847. So we're off by one part in 10 to the 13th from just 25 terms. Okay? So the answer was there. And all we did was to extract the answer by just doing some clever asymptotics. Yeah?
So do we just take enough terms so that the Richardson that we're using converges to some number
to our satisfaction? That's right. Mm-hmm. Okay, and of course you have to play. You have to make a table like this. And you see, when you do a second Richardson, that they seem to be hardly changing. They're only changing in this decimal place here. Okay, so they've settled down to 1.6449. Okay, it seems like they've settled down. Here they've settled down to 1.644934 something. Okay, and you notice these are going down, whereas these are going up. Okay, and this has settled down to 812, 842, 847. So it looks like this is leveling off at 8.4 something. Okay, and leveling off very rapidly. This is very rapid convergence. Yeah. Mm-hmm. If I follow this out to 30 terms, it won't change anymore. To this number of decimal places, it won't change. It gives us this is leveled off. If I go to 30 terms, this 847 will become 846, and that's it, or 848, and that's it. That'll be the end. It'll no longer change to 12 decimal places. It just won't change anymore. Okay, it'll just it's changing, and then from there on, absolutely flat. There'll be no further changes. Okay, it's pretty impressive, right? Yeah.
Is it any reason for taking only the even?
Oh no! I just did it just to make the table short. I mean, just to make it fit on a screen so you could read it. No, in fact, I would never just take the even ones. I take all the Richardsons, look at the table, and try to see what is going on. And this Richardson table is quite typical of the way this behaves. The point that I'm making here is that the series knew what the answer was. And all you had to do was to tickle it, okay, and to get it to tell you what the sum was going to be without actually calculating the sum. Okay. Yeah.
Don't construct R2 in this way, but instead I do the iteration. So just follow the first step, but use it on R1 and
over here. Oh, you mean, I understand.
Yeah.
You mean calculate R1, that makes a new sequence. Then calculate R1 of R1.
Yeah.
And you get a table almost identical
But
to this.
which would be more efficient?
Probably they will be identical.
Okay.
Probably they will be, I mean, not, they won't give you exactly the same numbers, but the behavior of the table will be identical.
Okay. And is it possible to evaluate how accurate you may get without even calculate these?
Not always. Not always. It is possible if you know all of the terms in the series. That is, if you know that the nth term if you have a formula for a sub n, the nth term in the series, if you know this function exactly, then you can do the asymptotics and you can answer the question. Okay? But if you only know, I mean, suppose you're a very hard-working guy Okay, and you work extremely hard, and you calculate 50 terms in the series. Okay, but only 50. You don't have a formula, and therefore there's no way of, unless you know the asymptotic behavior of a sub n for large n, you can't answer the question theoretically. You can only use elegant techniques like this and look at the table and see whether or not the table, this Richardson table, appears to be converging.
If I always know the asymptotic behavior of the sequence,
then you can answer that question.
Okay.
Then we can do an asymptotic analysis of the problem.
okay, thank you.
Okay? Okay, so have you used Richardson before? Almost certainly you have. Okay? Because if you have you done numerical integration? Have you done this? You haven't done numerics in this class. If you know how to do numerical integration of a function, one kind of numerical integration is called Simpson's rule. Okay, and Simpson's rule is the first Richardson of the trapezoid rule. Okay, if this means something to you, if you have learned a little bit of numerical analysis, if you do Romberg integration. Do any of you know Romberg integration? It's a very, very clever integration technique. How does it work? It says, I need to find the area under this curve. Okay, here's A, here's B, and here's some curve, and I need to find this area under the curve. Okay? Now, there are various fancy techniques, but what if we're feeling really dumb? We don't want to use a fancy technique. We don't want to go to the library, look up a fancy technique. What will we do? Well, a very simple thing to do is just to break up the region from A to B, okay, into, let's say, 100 points. N equals 100. Okay? And then use the trapezoid rule. So what's the, do you know what the trapezoid rule? Very simple. You just draw a trapezoid, and you find the area of that trapezoid, and then you draw another trapezoid, and we have 100 trapezoids, and we add up the area of those trapezoids, and that's it. That's our approximation. Okay, that's not a very good approximation, but it's an approximation. And this, we'll call that integral I 100. Okay? Now, we take 200 points, so we double the number of points. And we repeat the process. We call that I 200. Then we take 400 points. Okay? And we do this for a while. We say we calculate 6 or 7 numbers. Then what do? Very nice. We'll call this S1. We'll call this S2. We'll call this S3. Call that S4. And then we use Richardson to find out what we're going to get if you continue the process. So without using a huge number of points, I mean, to add up, 400 numbers on a computer, come on. I mean, the answer is instantaneous. It's lightning fast. So by the time we've calculated 7 or 8 terms in the series, and we've used Richardson to extrapolate what these are approaching, that will give us a fantastically accurate answer for what you get if you were to use a grid, okay, introduce a grid of millions and millions and millions of points without actually introducing millions of points. So you see how powerful this technique is. That's a really very powerful technique. Okay, now, let me summarize. Here is an overview of the course so far. Okay? And what I've told you is relatively elementary stuff, because what I've told you is how to sum a series if it converges. But the question is, how do you sum a series if it doesn't converge? Okay? Now, that's the really interesting question. So how do you sum a divergent series. And is that a meaningful thing to do? Okay? So here are some examples of divergent series. Okay? What if a guy walks up to you on the street and says, what do you get if you add up 1 minus 1 plus 1 minus 1 plus 1 minus 1? Okay, that's a divergent series. It's divergent. Why? Oh, I should ask you, why is this a divergent series? What's the definition of a divergent series? Right. That's exactly right. A divergent series is a series that is not convergent. Okay? So the point is, that's easy to define, a divergent series. What do you mean by a convergent series? Okay? A convergent series is a series by definition. The strict definition is this. A convergent series is one for which the partial sums converge as a limit. So the definition of a convergent sequence, okay, definition of convergent sequence is perfectly clear. Okay, so we know what a convergent series is, and if the partial sums do not converge, then it's a divergent series. So the partial sums of this series here are 1, 0, 1, 0, 1, 0, 1, 0, and that sequence obviously does not converge. So that's a divergent series. This is a more strongly divergent series. If I said to you, what do you get if you add 1 plus 2 plus 4 plus 8 plus 16? Okay, you would say that's obviously a divergent series. Terms are getting bigger and bigger. Okay, here's another one. 1 plus 1 plus 1 plus 1. There's a divergent series. Okay, here's another divergent series. Now I know what you're thinking. You're thinking, that's stupid. It isn't stupid. Let me explain to you why it isn't stupid. You might be thinking, come on, there isn't any difference between this series and this series. Why? Why would you think such a thing? Yeah, what would be?
We can rearrange all these terms.
That's right. To look exactly like that, right? We could group the terms together, and that's called associativity. So you learned when you were very little children, okay, you learned the 3 laws of arithmetic. You learned that arithmetic is associative and commutative and distributive, right? What do you mean by associative? You mean that if you have a problem A plus B plus C, that's the same thing as A plus B plus C, or you could write that as A plus B plus C. Okay, you can associate different numbers. You could first add the numbers B and C, and then add the number A if you wanted. Okay? What does commutative mean? It means A plus B is equal to B plus A. Okay? And distributive, that's a fancy law of arithmetic. That says that A times B plus C is equal to AB plus AC. And this is obvious. Arithmetic is obviously associative, commutative, and distributive. Right? Wrong. That's not true. Okay? It's only finitely associative and commutative. Okay, and distributive. We don't know if it's infinitely associative, commutative, and distributive. Let me give you an example. Okay, let's push this up. Okay, you remember yesterday we talked about the series 1 minus a half plus a third minus a fourth plus a fifth, and so on. Okay? And we found that this series converges. It's actually equal to the log of 2. However, if you believe these laws of arithmetic, I can show you that this series is equal to pi. Okay? Is that your favorite number? What's your favorite number? You don't think it's not pi? It must be. You must have a different favorite number. Oh, no, I don't want a complex number. But what's your favorite real number? How about 57? You like 57? Okay. This series is equal to 57. Okay? If you don't believe me, I will show you how this series adds up to 57. Okay? What I will do is I will commute the terms. And I will associate the terms. Now, you know that if I were to add up all the positive numbers in the series, if I were to add up all of the positive numbers, that is 1, a third, a fifth, and so on, what would I get? Infinity. Okay? And if I were to add up all of the negative numbers in the series, what would I get? It would still diverge, right? It would give me minus infinity, right? Okay, so this is the plan. I will make this add up to 57. Okay? How do you make the series add up to 57? It's easy. You add up all of the positive numbers until this sum of positive numbers just exceeds 57. This is just greater than 57. And I stop when I get a number that is just bigger than 57. Will that happen? Of course it'll happen, because the positive numbers are a divergent series. Okay? I take them in order. So I use the numbers in order until it's bigger than 57. Got it? Then I start using negative numbers. I add on the negative numbers, and I take negative numbers until it goes just below 57. Okay? So this is now just, I stop when this goes just below 57. Then I take some more positive numbers until it goes just above 57. But when it goes above 57, it'll go above 57 less than before, because I'm adding on smaller numbers. Okay? And then I take some more negative numbers until it goes below 57. So this process, here's 57. The first set of numbers is just above 57, then just below 57, then above 57, below 57, and it converges to 57 by construction. Furthermore, this uses all of the numbers in the series, necessarily, in order. Okay? So every single number is included in this process, and the series adds up to 57. So this proves that arithmetic is not commutative and associative. It's only finitely commutative and associative. So don't make any assumptions. So this is some stuff that you learn in high school, or maybe even junior high school, which is wrong. It's just not true. It's only true, you can only use associativity and commutivity if the series is absolutely and unconditionally convergent. This is a conditionally convergent series. Okay, yeah?
So what about distributivity?
Yeah, the distributivity, I'm going to argue, is a much more robust law. Of course, we don't have distributivity here because nothing is being multiplied. Okay? But I claim that this is a more fundamental law. Do you understand why? Because this involves linearity. Okay, we're assuming that multiplication is linear. And so I'm going to accept this law as a much more important and more powerful law, higher level law of arithmetic than these two. These just have to do with orders and groupings of terms. Okay? But you'll see what I'm talking about in a minute. Okay, so what I've said here is, however, divergent series are not bad. As you're going to see, you see this series here? Do you know what you get if you add up this series? You get infinity. There's nothing wrong with infinity. If you happen to add up this series here, you get infinity. Perfectly acceptable answer for the sum of a series. If you add up this series, you don't get infinity. What is that? You're right. This series, the sum of that series is -1. You're going to see that today. But if you add up this series, you really get infinity, and that's perfectly okay. Nothing wrong with that. Here's another example of a series that really is infinity. So the series 1 plus a half plus a third plus a quarter plus a fifth and so on, that series is called zeta of 1, okay, and that's infinite. Okay, so this series is infinity. And this is very useful, okay? Let me explain. I mean, this is very, are you interested in architecture? Is anybody here interested in architecture? No, this is a very important series because it's useful if you like making buildings, bridges, and things like this. So, for example, what if you want to build a bridge with blocks? Okay, you don't have any glue. You just have bricks. Okay? So let's suppose that one brick is 2 inches long. And it's a homogeneous brick. And here's the center of mass. So the question is, can I pile bricks on top of one another to make an overhang? Do you think I could make an overhang as big as, say, one brick? You think so? If I just pile up blocks. Not building it out, piling bricks on top. I don't mean doing something like a brick and then having a brick here and a brick here and then a brick on top of here. I don't mean that. I mean if I just pile bricks one on top of another like this, how big of an overhang can I make? Okay, well, let's see. So the center of mass of this brick is right in the center. So I could put this brick on top of that, right? And now I get an overhang of 1 inch. Okay? Now the center of mass of this object is right over here. Okay? You can just see by symmetry, the center of mass is here, which is 1/4 of one brick. So the distance to the center of mass here is 1/2. So that means that that since the center of mass is right here, a distance of 0.5, if I pile this and this on top of this brick, now I have an overhang of 1 plus a half. Okay? Now the center of mass of this structure is over here. So if I pile that on top of another brick, now the overhang here is 1 plus a half plus a third. And the center of mass of this object is over here, and the center of mass is 1/4 from the edge. So you understand this doesn't fall down because it's balanced on its center of mass. And these two don't fall down because they're balanced on the center of mass. And these don't fall down because they're balanced on the center of mass, and so on. So you can keep going like this. And if you add up all the overhangs, 1 plus a half plus a third plus a fourth, and so on, if you do that, then the overhang will be infinite. So you can build an infinitely long bridge just with no glue and no counterweights. The only problem is, there are two problems. First, you can't stand on the bridge. Okay, that's a bad idea. Okay. Secondly, the bridge is very high, but you have to be very careful about how you build the bridge because you have to build it from the top down. You understand, right? You put this on top of that, and then you put these two bricks on top of that, and then you pick up those bricks. But at least theoretically, we can build a very, very long bridge. All right. So divergent series are very useful if you like to build bridges. But this is what I want to talk to you about. I don't know how far we're going to get today, but I will try to show you some interesting things about divergent series. First of all, I have showed you, I've argued, that addition is not infinitely commutative. I'm going to show you today something called Euler summation and Borel summation. And then I'm going to talk about generic summation methods. But I'm going to emphasize that addition is not infinitely associative. Okay? And then I want to talk to you about zeta summation, and then I want to talk to you about continued functions. This is really the interesting issue. Okay? But what I want to start out doing is I want to convince you that I can assign a meaningful number to the sum of a series that doesn't converge. I want to show you that I can do that in some sort of meaningful way. And it will take me about a half an hour to convince you that I can do that. Okay, so let's see. Does this go up some more? Whoops. Okay, so first of all, I want to show you that it's possible to take a series that is not convergent, okay, and assign a finite number to the sum of the series. Okay? And the simplest way of doing this is called Euler summation. And this is what Mr. Euler says. Okay, it's perfectly silly. Okay, by the way, what I'm going to tell you is really silly looking, but I'm going to do it anyway. Okay, so Mr. Euler says, suppose you have a series A sub n, and suppose the series is not convergent. Not convergent. So Mr. Euler says, don't worry about it. Construct a function f of x. This is the sum from 0 to infinity. He says, construct a function f of x which is equal to, which is defined as the sum from n equals 0 to infinity of a sub n x to the n. Okay? And he says, you can do this. Notice I've used in fact, let's use an equal sign. Okay? So this has to exist. Otherwise, I can't write an equal sign. So we'll assume that this sum exists for x, say, less than 1. Okay? And then Mr. Euler says, let us define, we will define the Euler sum of the series, okay, the Euler sum of the series as the limit as x approaches 1 of f of x. Okay, that's a definition. Okay, so the question is, does this ever work? Okay, we don't know whether or not this idea works, but let's see. Let's take the simplest divergent series we can think of. Consider the series, so here's an example. Consider the series 1 minus 1 plus 1 minus 1 plus 1. Okay, like that. This is a divergent series. Mr. Euler says, let's construct a function f of x which is equal to 1 minus x plus x squared minus x cubed, and so on. Does this series exist? Does the sum of that series exist for x less than 1? Yes, it does. What is the sum of that series? 1 over 1 plus x. And then Mr. Euler says, take the limit of this as x approaches 1. And what you learn is that the Euler sum of the series is 1/2. Okay. I know what you're thinking. This is really stupid, and it's ad hoc, and it's, you know. Okay, but that's fine. We got an answer. All right, let's try a different method. Okay. Yeah. What does it mean? It looks completely ad hoc. It doesn't. It looks perfectly stupid. I mean, we made up. I mean, it's just magic, right? We just pulled out of the hat a random machine. This is a machine. We can call this the Euler machine for turning a divergent series that diverges, going chugga chugga chugga. And when you get done, you get a number for the sum of the series. It looks perfectly stupid. Okay? I mean, you look doubtful. Okay? And I don't blame you. But let's continue. Okay? I mean, let's just see. So I'm going to show you another technique. This is called Borel. Okay? This is Borel summation. So Mr. Borel says, suppose you have a series, sum from 0 to infinity of a sub n. And Mr. Borel says, note, what do you get if you integrate from 0 to infinity dt e to the minus t, t to the n? Do you know what you get? How do you do that integral? Or a simpler way to say it is n factorial. Right. Okay. Yeah. Okay. We just integrate by parts n times, and you get n factorial. So Mr. Borel says, oh, okay, that's cool. So 1 is equal to the integral from 0 to infinity dt e to the minus t, t to the n, over n factorial. That's an identity for all n. Okay? So Mr. Borel says, that's a very hard series to sum. Let's multiply every term in the series by 1. Can't hurt. Okay? Which we could rewrite as the sum from n equals 0 to infinity, a sub n times the integral from 0 to infinity dt e to the minus t, t to the n, over n factorial. And now we will do something very interesting. Mr. Borel says we will define the Borel sum of the series to be what you get if you interchange orders of integration and summation. Okay? So this is a definition. So Mr. Borel says, if you integrate the series, the function that you get, by summing up, by integrating last, okay, and doing the sum first, doing the sum of t to the n a sub n over n factorial. So this is some function here of t. If you integrate, we'll define, if this integral exists, we'll define that to be the sum of the series. Okay, that's just a definition. Okay? Now, Borel is obviously more powerful than Euler. Why is that? Because you see, it may be that this sum does not exist. If it doesn't exist, you can't do Euler. But you notice that the sum over here is a much more convergent sum because the nth term in the sum is now divided by n factorial. So this has a much better chance, this sum has a much better chance of existing than this sum. Compare this sum here with this sum here, this has a much better chance of existing. Okay, so I gave you machine number 2. This is the Borel machine. It goes chugga, 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 chugga. You put in the nth term in the series, and out pops the sum of the series. It's ridiculous, isn't it? But just for fun, let's see what happens. Just just let's be silly for a second. What happens yeah, question.
Do they give the same answer for the same sums?
That's funny. That's exactly what I was going to say. That's right. That's the obvious question, right? Because if every time I invent a new machine, we could have Euler, and then we could have Borel, and then we could have Schmolowitz, and then we could have Hassenpfeffer, and go on and on. And each time you invent a new machine, you get a different answer. This is stupid, right? So let's, just for fun, see what happens if you calculate the Borel sum of 1 minus 1 plus 1 minus 1, and so on. The question is, do they give the same answer? A very reasonable question. Okay? So what do you get? So Mr. Borel says what you have to do is integrate from 0 to infinity dt e to the minus t times the sum from 0 to infinity of minus t to the n over n factorial. Right? That's what you get if you do the Borel sum of that series. What is this? What is that sum? Say it again? No?
To the power minus 2.
That's right. It's e to the minus t. That's right. So this integral is e to the minus 2t dt, okay, which is 1/2. Unbelievable! Look at that. So when I sum the series using Euler, I get 1/2. But when I use Borel, I get 1/2. It must be just luck. Unless we can invent a generic summation procedure, okay? I mean, obviously, there are an infinite number of machines. You could make up one rule and another rule and another rule and so on, and this could go on forever. So let's try to make up a generic summation machine. And to make sure that it's generic, I'm not going to tell you what it is. Okay? It's a secret. It's just some random procedure. And I'm going to give it a name. I'm going to call it S for sum. But I'm not going to tell you how it works. Okay? That is, Mr. Euler was perfectly honest with you, and he said, this is how you do it. This is the recipe. Right? And Mr. Borel said, this is the recipe. But I'm not going to tell you the recipe. I'm going to leave it completely undefined. I'm only going to tell you the properties of this machine. And I'm going to argue that there are only two properties that a summation machine should have. Okay? So property 1, okay, the first property is that it should behave like a sum. So what does that mean? Okay? So this is some machine that takes the series A0 plus A1 plus A2 and so on and assigns a number to it called the sum of the series, S. Okay? Property 1 should be that if I sum all of these numbers, A0 plus A1 plus A2, and this exists, this is equal to S, it should be exactly the same as if I were to pull off the first number in the series, A0, and use the machine to sum up all the rest of the numbers, A1 plus A2 plus A3. Otherwise, this doesn't make sense. Okay? So I'm only doing a finite number of additions here. I'm just adding the first number to what you get, if you apply the machine to the rest of the numbers in the series. Okay? Does everybody understand? So that's a, I mean, if we don't have this property, then this is perfectly silly. Okay. What about the second property? Property number 2. Well, we know that addition is not associative and it's not commutative, but I would like to have linearity. Okay? So I would like it to be that if I calculate the sum of a series of the form alpha times a sub n plus beta times b sub n, that this should be exactly the same as alpha times the sum of a sub n plus beta times the sum of b sub n. This is linearity. So I would like my summation machine to have a linearity property and a summation property. I'm going to raise the board if I can. Let's see. Whoops. Let's see. Wait just one second. Let's see, put this up here. Okay. Those are the properties that I would like. Yeah. No. Oh, no. I'm not assuming commutativity or associativity at all.
So I mean, why did you commute A and B's?
I didn't. I'm not adding them up in a different order. These A's are all added up in one unique order. First you add A0, and then you add A1, A2, A3, A4. These are all added up in the same order, and these are added up in the same order. Alpha A0 plus beta B0. Next, alpha A1 plus beta B1. No. This is what distributivity says. This is what linearity says. I'm not changing the order in which I'm doing the sum. I'm not adding up the 0th term and then the 19th term and then the 14th term and then the 23rd term. I'm not doing that. Of course, that's what linearity says. Okay, that's
equivalent to commuting all of the
no. Oh no. I'm not adding them up in a different order. No. No. I have not commuted anything. They are added up exactly in the same order. Okay? Here is the 0th term. The 0th term is alpha A0 plus beta B0. That is the 0th term in the series. And next, I have the first term in the series. Okay? It is alpha A1 plus beta B1. I didn't interchange any. I can interchange these two if I wish, but no. I haven't interchanged anything. If I interchange, are you saying that I'm adding up the first term and then the 0th term? Oh, I wouldn't do that.
On the right hand side, you have B's
Yes.
to the right and A's to the left.
Sure. But this is in order, and this is in order. I have not changed the order.
There was some order between A's and B's.
Think about it. I have not changed the order at all. What I've done is use linearity. I've multiplied all of the terms in this series by beta, these terms, all of the terms in this series by alpha, and combined them. But I have not changed the order. I haven't combined the second term with the 14th term. I've kept the order of the terms absolutely pristine, unchanged. Think about it. Well, hang on a second. So the question is this a meaningful thing to do? Let's see if we can. Okay, let's see what happens if we, let me show you how I might use these rules to sum a series. Okay, so suppose I have a series 1 minus 1 plus 1 minus 1, and I want to add up the numbers in that series. This is the answer to the question that you asked me before, do I get the same answer? Well, I got the same answer, but why did I get the same answer when I did Euler and Borel? The answer is because, you're going to see, because Euler satisfies these two axioms of any summation machine, and Borel satisfies these axioms of any summation machine. So I'm going to use generic summation to sum this series. And I need to make only one assumption. The assumption is that if I apply my summation machine, I will get an answer. Okay? Let's assume that this summation procedure is powerful enough to give me an answer. So the answer is called S. So you know what I'm going to do. S is equal to this. Okay, it's equal to the sum of 1 minus 1 plus 1. But now, by axiom number 1, this is the same thing as 1 plus the sum of all the remaining terms in the series. Minus 1 plus 1 minus 1 plus 1, and so on. Okay? And by axiom number 2, by linearity, this is the same. I can factor out a number multiplying all the terms in these series without changing the order of the terms. And you know what number I'm going to factor out. What number am I going to factor out? Minus 1, sure. 1 minus S times 1 plus 1 minus 1 plus 1 minus 1. Okay? But this, by assumption, is S. So S satisfies the equation S is equal to 1 minus S. Okay, so therefore S is 1/2. That's why I got the answer 1/2, because generic summation says it has to be 1/2 without even knowing what the actual procedure was. I've only assumed linearity and, secondly, summation, that the process involved here is summation. Okay, now, we have a lot more to talk about, of course, but I want to show you one more calculation that you may find interesting. Yeah?
You may be planning to talk about something later.
Yeah, I'm going to talk.
But when you did the Borel summation,
Yep.
you communicated an integration.
Yes, I did.
Summation, and that was very reminiscent of derivative expansion and convergence.
This is correct, and in fact, there's a name for what I did. This is the inverse of Watson's lemma, which is a standard technique in asymptotic expansions of integrals. Okay, and it's a way of turning a convergent series into a divergent series and vice versa. This is the exact reverse of Watson's lemma, and I'll talk about that. We'll talk about that. Okay, but we don't want to get too fancy yet. Okay. So let me show you something weird. What do you get if you add up the series 1 plus 0 minus 1 plus 1 plus 0 minus 1 plus 1 plus 0 minus 1, and so on? What do you get if you sum that series? Well, let's do what Mr. Euler says. Okay, Mr. Euler says, construct the function f of x, which is equal to 1 minus x squared plus x cubed plus 0 minus x to the 5th plus x to the 6th plus no x to the 7th minus x to the 8th, and so on. Okay? Do you understand? This is Euler. Did you see that? See what I did? Multiplied the nth term by x to the n. So this is equal to 1 plus x cubed plus x to the 6th plus x to the 9, and so on, minus x squared plus x to the 5 plus x to the 8, and so on. Now, here, what did I do? I interchanged the order of summation. But that is perfectly valid. Why is that? Because these are Taylor series. And inside the radius of convergence, a Taylor series is absolutely and uniformly convergent. And therefore, the order of summation doesn't matter. That's one of the rare cases where the order of summation doesn't matter. Okay? Now, we can sum this series. What is the sum of that series? Okay, 1 over 1 minus x cubed. And what is the sum? Whoops. What's the sum of this series here? X squared times that. That's right. So I get minus x squared over 1 minus x cubed. So this is equal to 1 minus x squared over 1 minus x cubed. Right? And Mr. Euler says we have to take the limit as x approaches 1. But in that limit, the top is 0 and the bottom is 0. So what should we do? It's ambiguous, so we take L'Hopital's rule, right? So if I take the derivative of the top, I get minus 2x, and the derivative of the bottom, I get minus 3x squared. And now I take the limit as x approaches 1, and I get 2/3. And now you see why summation couldn't possibly be associative. Because if I were to associate the 0 with these terms over here and add up the series in a different order, I would reduce this series to the series whose sum we said is 1/2. Now the sum of this series is 2/3, according to Mr. Euler. Does that make sense? Maybe Mr. Euler is just giving us a stupid answer. So let's use generic summation to get the answer. So let's assume that the sum exists, and let's calculate the generic sum of the series 1 plus 0 minus 1 plus 1 plus 0 minus 1, and so on. Okay? Now, let's see. By axiom number 1, this is equal to 1 plus the sum of the series 0 minus 1 plus 1 plus 0 minus 1 plus 1 plus, and so on. Do you agree? That doesn't seem to have helped too much. This was axiom number 1. Let's use axiom number 1 again. Okay? Let's repeat it. Use axiom number 1. So that gives us, if we pull out a 0, that gives us 1 plus the sum of minus 1 plus 1 plus 0 minus 1 plus 1 plus 0. Aha! Without changing the order of the terms, let's use axiom number 2. Let's add this up without changing the order of the terms in the series. So I'll add up these 3 numbers, these 3 numbers, and these 3 numbers. That's just adding these numbers, one at a time. So what do we get? If you add it up, you get 3s is equal to 2. 3s is equal to 2 plus the sum of da 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 0, da 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 plus 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 0, and so on. Okay? But by the summation principle, 0 plus 0 plus 0, we don't have any problem with that. That's a convergent series. That's 0. So therefore, we conclude that 3s is equal to 2. This is just 0. So 3s is equal to 2, and s is equal to 2/3. Aha! That makes perfect sense. Do you see I did not commute the order of any numbers in the series? Okay? I never commuted the order of numbers in the series. I kept the order exactly right. I added up. Okay? So there seems to be, let me tell you what my conclusion is. I haven't yet shown you that generic summation in this sense is useful for solving physical problems. We don't know that. But what I've tried to convince you today of is that it is possible to invent a universal summation machine that in some reproducible and sensible way can assign a sum to a series that diverges. We do not yet know whether or not this is physically meaningful. Okay? So at this stage, think of it as a very interesting game. Okay? But I'm going to show you very soon, maybe by tomorrow, that in fact we can begin to get physically reasonable results out. I mean, we can actually use this to solve physics problems. Okay? You understand we're in desperate need of such a procedure because we know that perturbation series are typically divergent. Okay? All right. Yeah?
I'm still confused about what are these numbers that we got. Like, what is this half and what is this 2/3?
What does it mean?
Yeah, like if we add them, we will not get this number.
That's right. So therefore, you should never attempt to sum the terms in a series that diverges, because if you do, you will get nonsense.
So what is this sense? Like, what is...
So what we claim, let me give you a quick answer, okay, but you're going to see that this is...
I mean, like...
I understand your question. So the question is, does this have any meaning? Is it just a way of constructing a finite number that we're going to call the sum of the series? Okay, that's the question. Okay, so the answer to your question is, we're looking for an answer to a very, very hard problem. Well, we can't calculate the answer exactly, but we can find a representation of the answer as a divergent series. This series is divergent because we got this series using, how did we get here? We used perturbation theory. Okay? And this is a representation of the answer. And there's a problem here with English. Not mathematics, but with English. The English problem is that we use this symbol here. And that symbol suggests addition. Okay? You're not supposed to add up the series. Why not? Because if you do, you'll get infinity. Nevertheless, I claim this is a meaningful representation. And what we're in the process of inventing is a way of converting this representation into another representation of the answer, which is finite and meaningful, and is actually the physical answer to the problem. Okay? So this is a two-step process. We have a hard problem, and we want an answer. How do we get the answer? We do perturbation theory. Perturbation theory produces a representation of the answer in the form of a series which is divergent. So this symbol is a stupid symbol. We shouldn't be using that symbol. We should be using this symbol. Okay? Then, if we use this symbol, you wouldn't misinterpret this series as meaning that you should add it up, because you should never add it up. Okay? In fact, I began this lecture by saying, even if it converges, you shouldn't add it up. You should never add up a series. That's one of the dumbest things you can possibly do. Okay? So what we merely need to do is to convert this representation into another representation which is understandable. Okay? What's an example? Suppose I was looking for an answer to a problem and the answer was 1 over 1 plus x. Okay? That's the answer to or 1 over 1 plus epsilon. That's the answer to the problem we're looking for. But this is a very, very hard problem to solve. So we don't know how to solve it, so we use perturbation theory. Okay, and the perturbation series, this is the perturbation series, is that we obtain is the sum of -1 to the n times epsilon to the n. Okay, but the value of epsilon that we want is 3. So this is a divergent series. So do you have a trick of making sense out of our perturbation series? Yes, you do. A very clever idea would be to say, let's not set epsilon equal to 3 and sum the series. Instead, we'll take epsilon very, very small, smaller than 1, and sum the series. And we would get 1 over 1 plus epsilon. And now we set epsilon equals 3, and we get 1/4, and we say the answer is 1/4. Okay? So this is a representation of the answer which is not valid at epsilon equals 3. But by changing the representation of this into this form, now we can let epsilon equal 3 and get a meaningful sum of the series. That is a very simple version of what it is we are doing in a generic sense. Okay, now of course here it's perfectly understandable what is going on. But in more complicated physics problems, it's not quite as simple as this. It's much more complicated. Okay, but that is in effect what we're doing. And today what I did was to construct a way of re-representing the series and summing it and getting, assigning a finite answer to the sum of the series. Okay? That's the procedure. That's what we're after. That's what we're attempting to do. Okay? By the way, in some cases, I can prove that this procedure rigorously produces the physical answer to the problem. And I'm going to explain to you some cases. In other cases, I can't prove that. And so this is the best that I can do.
Okay.
So what's an example? In quantum mechanics, I can prove rigorously that this works. And in super renormalizable quantum theories, I can also prove this works. But in electrodynamics, although I can use this technique, I cannot prove that it works. So this is, this is where the mathematical physics is right now. We can't always prove that the answer you get is meaningful. Can't always prove it. It's not necessarily true that it's meaningful. Okay.
So just a
Yeah.
comment. In that example that you wrote down, we're essentially using analytic continuation.
That's right. So in order to go, so the point is that this is a function, 1 over 1 plus epsilon, this function here. This is a function that has an abstract existence in function space. This is one representation of the function that works for some values of epsilon. When I say works, is convergent for some values, but not convergent for other values. Got it? And what I did was, to make sense out of this problem, I used analytic continuation. Here. But we're doing something more subtle and fancier than just analytic continuation here. And this is not, by the way, this is not the only procedure that one might be able to use. This is just one example. I'm just trying to establish that there is a sensible way to assign a finite answer to the sum of a divergent series. Okay? Yeah?
Can you prove that the Euler-Borel summation, just that method, gives you the same answer as the general summation method?
Yes. The point is, if Euler works, if it exists, in other words, if this procedure is a convergent procedure that exists, if it works, okay? That is to say, if this function, if this limit exists, and if you can sum the series and so on. And if this function here exists, then you can show that Euler equals Borel. Okay? Always. Yeah?
Can you also show that all these machines will give the same answer?
Only if the machines are linear.
But this
Only if the machines respect.
what did those
Yeah,
two
not